Hi guys. So in this second part of video about DFS, I wanted to go through specific problems and their implementation. So more or less the same algorithms as discussed on the lecture part, but with like specific code this time. And I also tried to follow like good design principles. We'll see what I mean in a second. So basically, we have 6 problems today. First, asks us to write a program that can quickly answer queries of the form is vertex u an ancestor of vertex v in a rooted tree. So we have a rooted tree, and we want to quickly answer whether one vertex is an ancestor of another vertex. And you can see my code. It's not particularly generic, but it has like a very nice, potentially too nice structure. It's not something you want to write like exactly at the contest. At the contest, you are more likely to implement its way that cpalgorithms.com uses. Here we have like very specific function structure, like separate function for everything, sort of good design principles. And in this way, like main program gets really short. You just like, you read a tree, you compute input, entry and exit times, you read ancestor queries, you answer queries, and you print answers. So like anyone familiar with the problem will understand this part. And then you just have to look in the specific details. So you see like to answer queries, you need time in and time out, and time in and time out are computed here. If you're interested, you can go to this function and see the specific implementation. So it will create a timer, create 2 vectors, and then call DFS. And if you want to see the implementation of DFS, you can go ahead and see. So yeah, something like that. Because it's a tree, we'll represent tree like as vector of as adjacency lists, right? So entry at index I is an adjacency list of vertex with number I, something like that. And because it's a tree, one possible way to write DFS on a tree is without having an array of visited vertices at all, you can just pass one variable parent. Then DFS will say, well, it says it computes entry time here, exit time here, and then in like when it loops over outgoing edges, it just checks whether adjacent vertex is a parent or not. So if you make a DFS on a tree, you can ignore vector like bool visited or whatever, or colors, anything like that. You can just check against parent. So if you don't go to parent, then you don't get into cycle. So you don't go to visited vertex. So yeah, that's one of the tricks used here. Everything else is just like nice function structure. It's not particularly generic, and we'll see in a minute why, because like in the second problem, yeah, to compute entry exit points, we just had to timer. We initialize timer here, and then we just assign current value of timer, increment timer, assign current value of timer, increment timer. One reason why it was not really great is because next problem, like, again, requires a lot of functions. In particular, you have to write DFS again. And this time you need it differently. So in this problem, we want to find a cycle. So we need vector of colors. And because colors can be like only 1, 2, and 3, or 0, 1, and 2, you can like compress, use less memory, and code them with 1 byte long integers. People sometimes use char here, but it's not nice practice because char has issues with signs, etc. So I use fixed width type whenever possible. So yeah, here, like main function of find cycle runs a series of DFS. So loops through all vertices. If vertex is not visited, so color equals to 0, then we try to find cycle. And also, whenever we find a cycle, we can actually return cycle straight away. And cycle is a vector. Whenever we enter a vertex, we push it on top. Whenever we exit the vertex, we pop it from the top. So it's more or less a stack, but just implemented with vector to be faster a little bit. And then the inner structures, like you have to update colors. When you enter, it gets gray. When you exit, it gets black. And here you just see, like, if adjacent vertex is white, and you have to make recursive call. And if you found it, you can return it. If the adjacent vertex is gray, it means that you have a back edge. And somewhere in the stack, you have a cycle. It starts at this vertex. So you find this vertex, you erase beginning, and you return. And here you'll return. So you erase like that head of the pass, which is not a cycle. That's one possible way to do it. And then there's just nothing interesting. Again, a bunch of functions to print everything nicely, etc. Yeah, that's how you find a cycle. Here you need colors. You do something when you discover a vertex. You do something when you finish a vertex, and you do something at back edge. The next problem is bridges. We want to find bridges. General structure is the same. We copy it, I believe, compute times depth first search. I just copied it from the first problem. And then I have find bridges depth first search. Find bridges, and it also has to return bridges in sorted order. So this is the only reason why it's here. And here it's again a series of DFS. So for each vertex, if it's not visited, you run DFS with a bunch of parameters. And then you maintain minimum time that you can get on the back edge, minimum in entry time that you can get on the back edge in that subtree. And how you recompute it? Like here it's again a tree reasons. Let me think actually. Oh, okay, like we don't want to go back to parents, but we are interested in all other edges. So if vertex is not visited yet, adjacent, it means that it's white, and we just like, because that adjacent vertex counts into like entry point, we count it in minimum back time at that vertex. Otherwise, it means that this vertex is already visited. Oh, it's the other way around. Like it is already, if it's already visited, then we just count entry time. If it's not yet visited, then we want to go recursively call ourselves and then update like what is the minimum entry time that we can get on the, going from that subtree by min relaxation with minimum entry times that we can get from children, from all of children. And if it turns out that this time at adjacent, which was computed in this recursive call, if it's If it's bigger than entry time in the current vertex, then it's a breach and we place it here. So yeah, something like that. And more or less the same scheme will apply when we find cut points. So this is more or less the same with several exceptions, like you have to process root separately when you're interested in cut points because root can be a cut point. If root has like several different children that are visited in from separate calls, it means that there are two disjoint subtrees and root is a cut point as well. But this condition is like mostly the same if you switch here and here. Then let me actually want it. Okay. So it's more or less the same. You can see that this sign changes to strict equality. Not much else changes. So here we have initialized children. Here we add children. Yeah, it's more or less the same. You just again analyze entry and exit points. You can compute entry and exit points in a separate DFS call. So if you have this DFS pre-written, you can just call it and use time in later. So that's one way to compute count points and bridges. So bridges and count points, just in case you forgot, are the edges and vertices that make a graph unconnected, disconnected when they are deleted. And like these conditions, sort of dynamic programming on the graph for minimum entry time that you can get in that subtree, from that subtree, but it's a relatively simple one. These are just like book tricks, I don't know. Then in problems 5 and 6, you are interested in strongly connected components. So how to compute strongly connected components? You compute topological order, and you do this just by appending to order at the end. So when you finish vertex, you want to append it. That's what you do. And then you compute strongly connected components. From that order, you iterate in reverse topological order. Whenever you encounter a new component, you create it and you run DFS to find all vertices of it on a transposed graph. So this time around, whenever you discover a vertex, you push back to the current component. It doesn't matter actually if you do it here or here, but it's just like the common way to do it. And then you may be interested in condensation graph. The condensation graph, you computed strongly connected components. For each vertex, you then compute what is the ID of its connected component. Then you can, like for each edge, this factor loops over all edges. If the endpoints can belong to different strongly connected components, then you insert a corresponding edge into condensation graph. And the reason why it's inserted is because, like, to avoid duplicates, I use an ordered set here and convert to vector of vectors later. So that's why it's called pre-condensation and it's called condensation. You can convert an ordered set to vector just like so. So you take two iterators to begin to the end, and vector can construct from two iterators. Pretty much every STL how is it called? Container can construct from two iterators. It will just put all elements between inside of itself, right? So you can convert them really quickly, just like so, without an explicit for loop. Once you computed condensation, you're interested in all roots of the condensation. Condensation is like a directed acyclic graph, but not necessarily rooted. So you're just interested in all vertices of the condensation graphs that have 0 degree. And this is how you solve this problem. It has an interesting legend of like fire stations in Sudislau, but it's like not really relevant to the problem. So if you want to, you can read the explicit legend here, but if you don't want, then it's a quick explanation what goes on. In the problem number 6, you just want to count edges in the condensation graph. We actually already did it, so we just build condensation graph and count edges. Counting edges is really simple. You just add like the size of each adjacency list, and you just print it. So yeah, something like this. And you can see like some functions appear quite often. Like obviously, get strongly connected components is present both here in the previous problem, like a DFS which computes times is present like in A, C, and D. But we still have to pretty much every time to rewrite the main DFS. It's not really good. And the way to get around it is by using the visitor pattern. I will cover visitor pattern relatively shortly here. Like I want to solve every problem in this set using visitor pattern, but I only got time to solve like first one because I was implementing the pattern itself for a long time. So we'll see. So the following part of the video will be about how to build sort of your own library for graphs, which has like one DFS, and then you don't have to write DFS every time. You want to write, you will have to write a supplementary object that DFS will use to like do everything. And you'll see what I mean in a second. So not to write DFS all the time. What you want is to create a DFS visitor. Let me actually first go to the implementation of, no, actually let's use it, okay, of DFS. So DFS will depend on a bunch of parameters. I made it like template of everything. I'm not sure that it's the best way to do it. You probably can be smarter, but what's our? So it will takes in a constant reference to a graph. Obviously, we can't pass graph by a value because it's a heavy object. So we pass like we have to either pass by const reference or by pointer. And because we don't want to change the graph, we pass by const reference. Yeah, also this part is about like good design principles, or at least not bad design principles. So if you're more interested like in competitive style implementation, I suggest going to cp-algorithm.com. The links will be down in the description. They have like pretty lightweight DFS pre-written for all these 6 problems. So you may find this more useful than like implementing your own library. I think you don't like you don't even have to have a library, even if you're a grandmaster. I believe like Sasha Danluk did not have library for a very long time. He was on top 1 Codeforces without having a library or anything pre-written. But it's fun to make your own library. It's also useful like for software development in general to learn some patterns, especially like advanced ones that are used only like together with complicated algorithms. So I believe most of the people like senior developers don't know about visitor patterns, I think. So yeah, it's like pretty advanced topics here, both in object-oriented programming and in algorithms. So you pass constant reference to a graph, you pass visitor by reference because visitor can sometimes have like have an object inside of itself. And it has some context about what's going on so that it can process vertices. You potentially may pass starting vertex if you're interested in. So first of all, we initialize all vertices. Initialization is relatively simple. We assign color to white, and we use color. If you go previously, color is a enum class, and it's defined this way to protect from unexpected usage. So you can just say enum instead of enum class, but then you'll be able to convert integers cast ints to color and vice versa. It's not what you want in a protected code. That's why we use like enum class. And this is also why we have to use color, key white instead of key white. So that's definitely not something you want to use in competitive programming, right? Unless you have it pre-written, which opens interesting opportunities. Then like visitor initializes at every vertex. Then visitor can, if you are given a start vertex, then you want to start DFS from here, and you also want to like, do something with that start vertex with visitor. Then you loop through all vertices again. It's not really relevant what graph is. The only thing you want from graph is to have get vertices and get outgoing edges of some vertex. So you can have your own implementation of a graph that possibly like saves more memory or something like that. As long as it has like two methods, it will work. If the current vertex is white, so it's not yet visit, then we'll run a DFS visit. That's an inner function that first sets color to gray and calls a method of visitor that discovers vertex. So visitor is some class that has method discover vertex that potentially does something when it enters the vertex. For example, if you're interested in strongly connected components, then a corresponding visitor can append to the current component, strongly connected component. Or if you're interested in timestamps, then visitor discover vertex can say time in at vertex gets current value of timer. When you loop through our outgoing edges, you examine edge. That's a generic function. It's it's rare or something here, but sometimes you need to do something with visitor here. Then you check what's the color's destination. If it's white, then it's tree edge. You call corresponding method. If it's gray, then it's a back edge. You call corresponding method. Otherwise, it's a forward or a cross edge. You don't typically need to distinguish between them. So visitor has just such method. And once you process all outgoing edges of a vertex, once you process an edge, you can finish it. For example, if you're doing some DP, you may need transitions here in examine edge, and you may need transitions here in finish edge. When we are computing like minimum entry time that's reached from the subtree, it would go into finish edge method. And then we mark a vertex as black and we finish it. For example, if you want to compute topological order, then visitor finish vertex will push back into order, topological order. And if you want to compute timestamp, then visitor finish vertex will say like time out, get something, the current value of time, and then timer increments. So yeah, and you may say like having methods that get vertices and get outgoing edges is not particularly efficient, because like when you say graph square brackets at index, it creates reference. But there's nothing wrong, like we can return a reference ourselves, or even better, graph outgoing, get vertices and get outgoing edges may return iterator range. Iterator range is a common concept. Basically constructs from two iterators, has two methods, begin and end. And because of these two methods, range-based force work. So range-based force can work with any object that has methods begin and end that return some iterators. So it will take this iterator, start here, increment until it gets equal to end. It's a really lightweight way to create ranges. So actually, these methods, they return like an object that takes constant space. So they are pretty efficient. Also, just for convenience, you can like not to have terribly long names. Like, I don't think you want like iterator range of vector edge constant iterator. So you can just shorten some of the names sometimes with using and type name, something like that. And like this is an interface, as you probably guessed. It does not implement everything. It has purely virtual functions because there is no like typical implementation of a graph. You can have adjacency metrics, you can have adjacency list. Sometimes your vertex are not like objects indexed, not indexed objects. So you can have actual graph as a form of unordered map between vertices and edges, something like that. So that's why it's an interface, and it's abstract interface because there's no like default implementation of a graph. Unfortunately, because of that, I have to write maybe unused all the time, but it happens. Also mark as many since const as you can. So it's not expected from getters to change anything, so that's why they're const. And also I return constant iterator so that nobody will change anything, even though we return like access to our memory. And also we have a simple interface for graph, for edge. It has like source and destination. Sometimes, because there's no like a universal way to implement edges, sometimes you may like only be concerned with destination of an edge. Sometimes you want source and destination. Sometimes you want source destination weight. Sometimes you want source destination weight color. And the list of the parameters may grow rapidly. So, but at least we need destination because we want to be sure that there's a member of this class named destination so that our DFS can actually work, because it has to go to destination, right? So that's why we require destination here. I'm not sure why I require source here, but usually you need source as well. Huh. I'm not actually sure. Yeah, let's leave it not to break anything. And then like, we already went through all of the methods of DFS Visitor. It's also an interface because you require some methods to be there, but this time you don't actually require them to do anything meaningful. It may happen that for whatever algorithm you write, it does not care about forward edges. So there is a default implementation which is like empty, do nothing. It's possible. Wait, like you probably won't pass exactly that visitor, but we don't want you to redefine every method, to overwrite every method. So we leave empty implementation by default. Because of that, we also need like maybe unused everywhere, but I guess you have to deal with it if you want everything implemented in a nice way. You also don't return anything. Like if you want to get something out to the visitor, you just add private or public fields, members, and then you just work with them. So what we'll actually need to define, like all of that part can be pre-written, right? What we actually need to define for a specific problem is you want some type for vertex. And it's not necessary to like define specific type for vertex. You can just use int everywhere else, but I like it this way more. Edge in this particular case is just interface. It does not add anything to edge. I don't want to write like template parameter all the time, so I made like using statement. Graph, like this is a typical implementation of a graph that can also be pre-written. So it has a constructor from the vertex count. It's just single integer. You copy to vertex count. You resize your array of vertices and ongoing edges. For convenience purposes, we store IDs of the vertices in case you ever like want something strange. You can have it. You have an add edge method because it's like mostly used, but not like 100% necessary. I guess like in some other graph interface, you may ignore this method. I think so. But it's usually like used. So I was not sure whether or not to include it into the interface, so I left it here. And we have several methods that override previous methods. So they will just, if you look further, they just return like iterator range constructed from 2 iterators. So nothing smart here. This can also be proven. Then you have time DFS Visitor, and basically like everything above can be written, and actually this can be pre-written. The time DFS Visitor implements interface. It has it overrides only 2 methods. It has timer inside of itself. It has time in, time out, and for convenience, vertex count, although you can ignore it, I guess. I guess you can. Like this. Why not? Yeah, so it's really short. It has like one counter, 2 arrays, and 2 methods. At the beginning, you like get memory for these arrays. And then you override, you want to do 2 things. One when the vertex is discovered, and next is when vertex is finished. So discover vertex increments timer by 1 and writes it into time in. Finish vertex increments timer by 1 and writes it into timeout. Although these operations are actually done in different order. So you take the current value of timer, then increment it by 1, but this statement returns previous value of timer, so it goes here. It doesn't matter, you can write ++ timer, but then timestamps will start from 1, and this way timestamps start from 0. It's useful when in something like last common ancestor, when you want timestamps to be actual indices. So again, like this method is like the only thing you implemented to get timestamps out of DFS. It's automatically used here. And finish vertex you also implement. And with that, like main code, I did not actually bother this time with input output because I don't know what's or what. So here's input. here's like outputs. So you make decision based on like 2 lines long if statement, and all DFS happens here. I'll show you. You created a graph, you created a visitor, you called DFS. And that's it. And actually, I was not sure like what is the correct way to put DFS. Like DFS actually possesses the memory, right? Owns the memory. DFS owns color maps, so map of colors. I'm not sure that this is like correct way. I'm most probably sure that it's not correct way. I guess there's like better way to encapsulate memory. But I couldn't think about it just yet. I'll probably rewrite this part because it's kind of not the interface I would like to see. So you kind of have to create an object of class DFS to run DFS. The reason why, because I did not want to pass color map all the time to DFS visit. I wanted DFS to like, yeah, I basically don't want to pass a color map all the time. And this is why I implement, like, I just encapsulated everything into class, like memory of colors, main function of DFS, and DFS that visits specific vertices. I don't think that it's the best implementation, but like by the time I got previous parts of the template working, I was not in particular in the mood of thinking a lot. So for now it's implemented this way. It will probably change. And the point of this entire story is that if you ignore output and input, then your main gets very short, and all the code above, outside of the main, can be pre-written. And if you need new DFS, you don't write DFS, you write new visitor. You can overwrite only the methods that you want to overwrite and leave other methods as is, and it will work. You don't have to, like, every time remember what is the condition for tree edge, for back edge, for other edges, and you don't want to, like, you don't have to think about these conditions when you write DFS. You know that you want to do something when the edge is a back edge because it creates a cycle. So you just override this method, do whatever you want to do, and you're sure the DFS will call this method only when it's necessary. So it's a really great pattern. Sometimes writing visitors can be tricky, but it's also a great mental exercise. Once you implement like 10 or so visitors for different problems, it gets more or less straightforward. And actually, you may think like this is something strange, like I haven't ever seen this in my life. You may think. The truth about this, if you know something about C++, you may also know something about Boost, which is C++ libraries. And the truth is, I somewhat copied them, but not exactly. Because, like, I agree that some parts of it are strange, but usually it's great. So Boost is a very popular set of libraries for C++. In particular, they have modular bound graphs. And you can see that their DFS is implemented in the exact way that we did. It's not actually something strange. Here you can also see an example of entry time, exit time, and also parents. So like example of what you can compute at the three edges is array of parents. These are not computed by default, but they are predefined visitors. And this is the entire point. So by default, your DFS does nothing, and it does not do any extra work. Whenever you want to do it, something, you can use predefined visitor, like predecessor recorder or parent, actually, parents or times. You can use that visitor. So if you have a lot of visitors implemented already, then you just use them. And you don't think about what you have to do. You just know that you can compute this. And instead of copying your DFS, you, for example, copy your visitor. I don't know, it's kind of simple. And like specifically, visitor is just, well, that's a concept that has more or less equivalent of interface. It implements several methods, like initialize, start vertex, discover vertex. It's all the same that we see. Only here they pass graph. I think it's sometimes useful, but I don't think like it's always useful. I mean, I did not include it to my codes because I think you don't need this actually, and you can go away with plain DFS, but I guess not always, like if you want something really complex. And you may have to do this. But I'm not sure that this is necessary, to be honest with you. But you may pass graph to methods of visitor as well. So I just copied all of this into a template and then implemented what I wanted to do. And now I can reuse that visitor again in the next problem. And potentially, like once I solve all of these 6 problems, I will have like a bunch of visitors in Git library that I can like copy paste entirely and then just call methods of it instead of writing DFS every time. And for simple DFS, it does not matter, but for more complicated DFS, that you have to do something with edges so, with edges tree, with edges back edge, and etc. But like writing DFS all over again, it's not a good practice, right? It's code duplication. So yeah, that's why people invented DFS visitor pattern. It is actually defined like in a different way. Some of the template types can be derived from graph. Graph supports it. So yeah, but if you want like lightweight version without much of that stuff, then you can just make everything a template parameter. Yeah, something like this. I find this like very interesting pattern. I don't think like many people teach about it, but at the same time it's important, so I wanted to cover it. So far I only have like one problem implemented with it. I will definitely try to implement more today, but I just wanted to give you a general idea because new visitors won't be different, and that's the point. Like I feel like if I will just show you 10 visitors, one gets the idea, because you will think like about what are the differences between different visitors, whereas you should think about what is in common. They all used in the same way by DFS. DFS just calls their methods. And what all that you have to think about is what method to overwrite and what to do in this overridden methods. So yeah, that's what I wanted to say for today. I guess I'll publish solutions with visitors as well, like later today. So yeah, thanks for watching. Hope you enjoyed. Hope it helps. Like this is not something trivial. Not sure that there are like many videos on YouTube about that, since there are very little videos about something advanced as such. I mean, there are not many good videos about DFS in the first place, right? I mean, non-trivial applications, like not only DFS, but also externally connected components. There are not many great videos simply. And for sure, there are not many great videos about visitor pattern. So yeah, that's something interesting I wanted to talk about today. Again, thank you very much for watching. And if you want to know like when these videos come out, you can join our Discord server. I guess like link is somewhere down in the description, should be. So yeah, if you want to get like notified when a new video comes out, actually sometime in advance before it comes out, you can join our Discord server. I'm usually there. I can answer your questions about like specific problems, something like that. You can chat with other community members. I think we have like around 100 people already. So yeah, you're welcome to join. And if you ever get tired of watching my videos, you can always go to like to the main page of my channel and then to the channels tab. And there are like 8, I guess, channels that I find interesting. So whenever you get tired of watching me, you can always watch other guys. I mean, this is something that I personally watch, so it makes sense. If you're interested, you can check this out. So yeah, but for today, that's it. Thanks for watching and bye-bye. See you next time.